we would like to finish the discussion on words and disambiguation and touch upon the algorithms which are based on semi-supervised and unsupervised learning. In particular, we would like to make some summarizing remarks on how supervised, semi-supervised and unsupervised algorithms relate to each other and how do they compare. Then we will move on to our work on resource constraint words and disambiguation, which is a very important line of work for languages which do not have lots of sense smart corpora and there is absence of resources for these languages. Indian languages fall in that category, and we have done some pioneering work in the field of semi-supervised and unsupervised words and disambiguation, where the resources are scarce. So far what we have seen is that we have looked at a number of words and disambiguation algorithms based on the idea of overlap, which essentially takes the context words and then sees the overlap of these words in the sense repository of the word net. So, one fundamental point to remember is that the words in the neighborhood of a target word undergoing disambiguation are the most important clues for word sense disambiguation. All right. So, these words form the feature vectors for supervised machine learning based algorithm for word sense disambiguation. They form the overlap for knowledge based, overlap based word sense disambiguation algorithms, and also the context clues for unsupervised word sense disambiguation algorithms. So, as is intuitively clear and which probably does not need too much of reiteration, that it is the words in the neighborhood of the target word that have to provide the clues for disambiguation. So, in the last lecture we had seen k nearest neighborhood based words and disambiguation. We will very briefly look at two more algorithms and then move on to semi-supervised and unsupervised algorithms for word sense disambiguation. So, going to the slides, we see that our topic is word sense disambiguation, semi-supervised and unsupervised methods, and moving on to resource constraint word sense disambiguation. So, since the words in the neighborhood of the target word provide the contextual clues, they are used to form the feature vector, and once a feature vector is formed, then the task is, let us say, 3/4 done, because after that it is only the problem of finding a machine learning algorithm, a suitable machine learning algorithm that will place a label on the word in terms of its sense, or will place the word in a class, the class being a sense for the word. So, if we look at the title of this slide, words and disambiguation using SVMs, support vector machines. The support vector machines form a class of powerful classifiers which find a hyperplane with the largest margin that separates training examples into two classes. So, this falls in the category of a large class of classifiers which set up hyperplanes to classify the positive points from the negative points. As SVMs are binary classifiers, a separate classifier is built for each sense of the word. In the training phase, we have to use a tagged corpus for every sense of the word an SVM is trained using the following feature: part of speech of W as well as part of speech of neighboring words, local collocations, co-occurrence vectors, features based on syntactic relations, for example, head word, pause of head word, voice of head word, and so on. So, as is well known in supervised machine learning algorithms, it is the feature vector which is the most important component of the training scenario. The richer the feature vector, the more effective is the learning algorithm. So, that is why we see that in the training phase there are a number of features of the target word as well as the neighborhood words which are considered. In the testing phase, given a test sentence, a test example is constructed using the above features and is fed as input to each binary classifier. The correct sense is selected based on the label returned by each classifier. So, this shows what is done in the SVM based classification. SVMs have become very important for text processing, text mining, text information extraction applications, and therefore, it is not a surprise that SVMs are being tried for words and disambiguation also. Now, words and disambiguation using Perceptron trained hidden Markov model. Here the task of words and disambiguation is looked upon as a sequence leveling task. The class space is reduced by using WordNet super senses instead of actual senses. A discriminative hidden Markov model is trained using the following features: part of speech of word as well as part of speech of neighboring words, local collocations, shape of the word and neighboring words. And this algorithm is also quite suitable for named entity recognition labels like person, location, time, etc. And they make use of a powerful idea called the super sense tag set. All right. So, with this we will close the discussion on supervised machine learning algorithm for words and disambiguation, and would like to proceed to semi-supervised and unsupervised algorithms. But before that, a table on remarks on comparison of supervised approaches to words and disambiguation. So, if the approach is naive Bayes, then the average precision is seen to be about 64%. Average recall is not reported in the literature. The corpus used is sense eval 3 all words task, and the average baseline accuracy for this task is about 61%. So, the naive Bayes algorithm improves on the performance of baseline by about 3%. If the approach is decision list based, then we find that the average precision is very high, 96%. Average recall, this question is not really applicable here. The corpus was used such that there were 12 highly polysemous English words, and the testing was done on that. The baseline accuracy is 64%, and therefore, the average precision is really very high compared to the baseline accuracy. Exemplar based disambiguation, which is k nearest neighbor, precision is 69% or so. Recall is not reported, and the corpus is Wall Street Journal corpus using 191 content words. The baseline accuracy is reported to be 64%. So, there is about 5% improvement in accuracy when one uses this algorithm. For SVM based approach, the accuracy is 72%. Sense eval corpus is used, and 57 target words are seen, and we find that the average baseline accuracy is 55%. Therefore, the improvement is in accuracy is about 27%, no 17%. Then Perceptron trained HMM gives an accuracy of about 67%, baseline is 61%, corpus used is SensiVal3, this is all words the disambiguation task, and again the accuracy improvement is about 7 to 8%. So, what do we summarize from these observations? We find that supervised learning algorithms go to achieve an accuracy of about 65% or thereabouts, and therefore, this is a good powerful approach for Watson disambiguation. Any performance above 65% is good in Watson disambiguation. However, as has been said, the constraint of using supervised algorithm for Watson disambiguation is that we need large amount of training corpus, and that is time consuming, labor intensive, money intensive, and it is not an easy matter. So, can we do something about this very valuable resource called SenSmart corpus? Can we, for example, not have a very large amount of training corpus, but start with a seed amount? Can we do completely away with training corpus? So, these possibilities need to be examined, and that is the next part of the discussion. So, semi-supervised approaches. The first algorithm is semi-supervised decision list algorithm. It is based on YAROWSKY'S supervised algorithm that uses the decision list. So, we need to train the decision list algorithm using a small amount of seed data. So, in all semi-supervised learning algorithms, there is one uniform idea. The idea is that we use a small amount of training corpus. This training corpus is used to train a machine for the task involved. After the machine is trained, it is used to tag the unseen corpus. The unseen corpus is tagged, but there surely is some amount of error, because the training was done on a very small amount of data, and it was not possible to look at every region of the concept space. So, semi-supervised learning algorithm typically entails a phase of tagging followed by manual correction. Once manual correction is done, the machine is retrained with larger amount of training data, and this procedure continues: tagging, manual correction, retraining. This cycle continues until we achieve the desired level of accuracy. So, this we can summarize by writing on a piece of paper basic idea of semi-supervised WSD is that have seed training data, tag, no, first train using seed data, then tag unseen data, manually correct tags. Step 5, retrain using larger data, repeat steps 3, 4 until satisfactory accuracy level is reached. This is the main idea of semi-supervised learning algorithm in any domain, and worst sense disambiguation also follows the same path. Now, a diagram on the slide shows this picture: initialization, progress and convergence. So, this has some similarity with, for example, how vegetables grow from seeds. So, there is a small amount of seed data, and that is used to populate terrain using the seed data, and we obtain larger vegetation. The seed set gradually grows, and we stop when the residual set stabilizes or when the learning algorithm correspondingly converges to acceptable level of accuracy. Some remarks on semi-supervised approaches are the following. Semi-supervised decision lists have an average precision of 96%, tested on a set of 12 highly polysemous English words. The baseline accuracy is about 64%. Semi-supervised decision lists give that kind of accuracy, 96.1%, and tested on the same data. Average baseline accuracy of course remains the same. And what we find that semi-supervised decision list algorithm works at par with the supervised version, and it needs significantly less amount of tag data. So, proceeding further, we go to the topic of unsupervised approaches to worst sense disambiguation. The attraction of unsupervised approaches is that there is no dearth of electronic corpora in any language. However, creation of sense smart corpus is expensive, as has been already said. So, there has been a large body of work exploring whether or not it is possible to do worst sense disambiguation in an unsupervised setting. The key question there is the following. We will write it down. Key question in unsupervised WSD. We will put a star on this. How to put the sense level on the word when the training data did not have any label. This is a key question. How to put the sense level on the word when the training data did not have any label. So, that is a key question in any unsupervised setting. When we have not used any label in the training phase, how do we suddenly invent labels to place on the words? So, this problem is solved by having a lexicon of labels. Okay. They are not used to mark the training data, they are used to produce the labels once we have determined the sense of the word. So, there is this question of going from the decision of the sense on the word to the label on the word. Okay. This bridge needs to be closed, this gap needs to be closed. All right. So, for the unsupervised approach, we discuss a well known work called the Hyperlex algorithm for unsupervised WSD. This was published in 2004 in the journal Computer, Speech and Language. The author is YAROWSKY'S. So, the key idea here is described. Instead of using dictionary defined senses, extract the senses from the corpus itself. These corpus senses or uses correspond to clusters of similar contexts for a word. So, this idea we have met before. We have met before in the supervised setting. The idea was used in decision list based words in disambiguation. We had taken this example of plant, where plant has the meaning of manufacturing or it has the meaning of vegetation life, okay, flora. So, plant has one meaning of being a small tree or being a manufacturing plant. Now, in this case the decision list was formed using the collocations, the words in the context. However, there a label was used. Okay. After watering the plant, it slowly bloomed. After watering the plant, it slowly bloomed. So, let me write it down. The word is plant, sense 1 after watering the plant bloomed. Sense 2, the chemical manufacturing plant was built in 2 years. So, the word to be disambiguated is plant, and the very important clues for sense 1 are water and bloom. Very important clues for plant here is manufacturing, build, chemical and so on. Now, in unsupervised learning algorithm, what we will do is that if at all we find in the test sentence these words coming in the context of plant, water, bloom, etc., in the test sentence, then we latch on to this sense 1, and opposite will be the case if we find chemical, manufacture, build, such words in the neighborhood of the word plant. This is a simple idea, and different algorithms try to capture these neighboring words as contextual clues. So, the same thing is expressed here in the slide. Key idea is that instead of using dictionary defined senses, extract the senses from the corpus itself, which is nothing but the context words. These corpus senses or uses correspond to clusters of similar contexts for a word. The paper discusses the idea with a French example. The example here is water, the French word is eau. So, first of all, what happens is that we create a graph with collocating words. So, this shows a connected component of the graph, where collocated words like river, water, production, irrigation, flow, electricity, etc., come together. There is another connected component in the graph from the contextual words, where we find the word cup, match, team, football, victory, etc. coming together. So, you can see that the word cup, which has many different senses, here cup means a trophy. These senses come together or the sense comes in association with senses of words like victory, team, football, world and so on. And the water sense of the word U comes with the words river, irrigation, production, electricity flow, which together form a coherent sense graph. Now, the target words give rise to what is called the root hubs. Different uses of a target word form highly interconnected bundles or high density components. And in each high density component, one of the nodes has a higher degree than the others. So, first we construct the co-occurrence graph. That means, we take the words which are contextually related meaning wise also, arrange the nodes in G in decreasing order of in degree, select the node from G which has the highest frequency. This node will be the hub of the first high density component. Delete this hub and all its neighbors from G, repeat step 3 and 4 to detect the hubs of other high density components. So, here is an example of the word barrage, which is getting disambiguated. The word barrage has 4 components in the sense of sense association graphs. So, one component is with the sense of water, where we find the words construction, engineering work, river, project, reservoir, flood coming together. The other component has the sense of vehicle and the associated senses, vehicle, truck, member, driver, policeman, group, they come together. Then there is association on the frontier sense, where we have Algeria, military, efficiency, army, Switzerland, post. These are very strongly associated words. They come together to form a sense component. Then match. Here the correlated words are winner, victory, encounter, qualification, shot, soccer, etc. So, we find that the word barrage can participate in one of these 4 connected components as sense subgraphs. Then there is this stage of delineating the components. Attach each node to the root hub closest to it. The distance between 2 nodes is measured as the smallest sum of the weights of the edges on the path linking them. The concept of weights will be explained in the discussion coming after 2 or 3 slides. So, the delineation involves first step, add the target word to the graph G, and step 2 is compute a minimum spanning tree over G, taking the target word as the root. So, spanning tree, it would be remembered, is a part of the graph which covers all the vertices, but may not cover all the edges. So, this is a part of the graph which is cycle free. Now, what happens is that after delineation we discuss disambiguation. Each node in the minimum spanning tree is assigned a score vector with as many dimensions as there are components. So, barrage for example had 4 components. There are these formulae which are empirical in nature, and we will not go into the details of how these are obtained, but some amount of intuition can be given. DHIV is the distance between the root hub HI and the node V in the tree. So, the sense of the word V is SI, which is equal to 1 by 1 plus d h I comma v if v belongs to the component I, otherwise it is 0. So, it is easy to see what is going on here. We find the distance of the word from the cluster. Okay. So, we explain it diagrammatically. So, what is happening here is that if I take the word barrage, so there is a component with water, project, river and so on. Let us call this component C 1. Another component with vehicle, truck, driver and so on. This is component C 2. Another component C 3 with the sense of frontier. Okay. And it has military, then army and so on. Now, when this word barrage is seen, we see from the context words of barrage in the test sentence which component it is close to. Okay. Suppose the context words of barrage in the sentence are such that the distance of the neighborhood words and of barrage from amongst these components is the least for C 2. Then we know that we have the vehicle, truck, driver, etc., as the strong association of barrage, and root sense is the winning sense for the word barrage. So, this is really a cluster based algorithm, and intercluster or distance from the cluster is the guiding factor for the algorithm. The minimum spanning tree essentially facilitates finding the distance of the word in that context from a particular component. So, now we discuss the weight value. Weight value is 1 minus maximum of P A given B comma P B given A, which is a probability value. The probability of A given B is computed as frequency of A and B together divided by frequency of B, and probability of B given A is frequency of B and A together divided by frequency of A. So, here the probability of U given average is 183 by 479, which comes out to be equal to 0.38. Probability of average given U is 183 by 1057, which comes out to 0.17. So, weightage is equal to 1 minus 0.38, which is 0.62. And this table shows the values for other components for the senses in discussion, and from this it is possible to identify the distance from the sense cluster in which we are interested. So, here is an example for the word barrage. The French sentence is given here, and the English sentence is the dam collects water during the rainy season. So, here we find that water is the winner in this case. So, the component which contains water is the winning sense, and that determines the sense of the word barrage. So, some of the critiques of this algorithm is that it makes use of the small world structure of co-occurrence graphs, The good part is that it does not require any tag data, automatically extracts a use list of words in a corpus, does not rely on dictionary defined word senses, because there is no training corpus. The bad is that the classifier is word specific. A new classifier needs to be trained for every word that we want to disambiguate. The average accuracy is 96% when tested on a set of 10 highly polysemous words. There is another famous algorithm, unsupervised WSD. This makes use of the ROGET'S thesaurus categories. It is based on the following three observations. Different conceptual classes of words, say animals and machines, tend to appear in recognizably different contexts. Different word senses belong to different conceptual classes. For example, crane, which has the sense of machine and bird. A context based discriminator for the conceptual classes can serve as a context based discriminator for the members of those classes. So, we first identify the salient words in the collective context of the thesaurus category and give the weight appropriately. Weight of a word is salience of the word, which is the probability of the word given the category divided by the probability of the word. So, here are some examples. Words like species, family, bird, fish, egg, coat, etc. They are shown, and we give the salience values in the bracket, which are based on the probabilities, which in turn are based on frequencies. Similarly, there are words in the tools and machinery domain along with their salience values. So, here how does the disambiguation algorithm work? Predict the appropriate category for an ambiguous word using the weights of words in the context. So, we have to obtain the category and the argmax is based on the category. The Bayes theorem is applied, therefore, we have prior probability, probability of R cat into the likelihood probability, probability of word given the ROGET'S category. Here is an example: lift water and to grind grain. Treadmill attached to cranes were used to lift heavy objects from Roman times. So, here the word to be disambiguated is crane, and we find that in the context there are very strong clue words like water, grind grain, treadmill, lift heavy objects, and so on. So, we take the words from the tools and machine domain. The word lift has a weightage of 2.44, grain has a weightage of 1.68, used has a weightage of 1.32, heavy has a weightage of 1.28, and so on. And crane can also belong to the animal insect domain, where we have the contextual clue words like water. So, water for example, is drunk by animals and insects, and the weightage for this word is 0.76. So, the weightage, combined weightage of clue words coming from machine domain is 11.30. Combined weightage of clue words coming from the animal insect domain is 0.76. So, clearly this is the winning value, and the domain automatically shifts to the machine domain for the word crane. The remarks on this particular algorithm, which was quite famous at some point of time, is that there are good points about this algorithm. Lexical network, that is thesaurus plus corpus is used. So, it is an unsupervised learning algorithm, but making use of a lexical resource. He is able to capture the clues provided by proper nouns from the corpus. For example, Sachin Tendulkar will have a strong salience value in the category sports. The classifier is not word specific, will work even for unseen or rare words. The bad aspects of this algorithm are: the performance is weaker for minor sense distractions within a category. For example, two senses of drug in medical domain. So, if the polysemy is such that there is very little sense distinction between the two senses, okay, these are shades of senses, then this algorithm does not perform very well. It does not perform very well for idioms. For example, the word hand in on the other hand or close at hand, the algorithm will not give the correct sense. The average accuracy is 92% when tested on a set of 12 highly polysemous words. There is another approach called Lean's approach. So, the basic idea is that two different words are likely to have similar meanings if they occur in identical local context. Two different words are likely to have similar meanings if they occur in identical local context. So, if you take the word, the facility will employ 500 new employees. The senses of facility are installation, proficiency, adeptness, readiness, toilet or bathroom, and in this particular case the sense 1 of installation will be the winner sense for the word. The subjects of employ can be words whose types are organization, then plant, company, industry. It can be unit, aerospace, memory device, pilot and so on, with different weightages as shown here. The similarity is computed between the target word and the words in the sense cluster. So, if A is hill and B is coast, then the commonality between A and B is that A is a geoform and B is a geoform. So, hypernymy is used for computing the similarity between a word and a sense component where it belongs. So, the words from the sense component are taken and similarity is computed between the target word and the context words. So, this gives rise to the determination of the sense. Words and disambiguation using parallel corpora has become quite popular these days because of the advent of the field of statistical machine translation. Large amount of parallel corpus is getting created, and these parallel corpora are good for determining the sense of the word. Okay. So, the contextual word produces the clues, and the sense level comes from the parallel aligned sentence. So, the sense of a sentence can be obtained given the aligned sentences. So, here is the description. A word having multiple senses in one language will have distinct translations in another language. This is a very powerful clue based on the context in which it is used. The translations can thus be considered as contextual indicators of the sense of the word. So, there is a probabilistic formulation for this. The sense is T, its manifestation is word E, W E, let us say in English, and word S in another language S. So, probability of W E, W S and T, this is a joint probability. This can be written as probability of T into probability of W E given T into probability of W S given T using the independence assumptions. So, W E and W S do not have any dependence on each other. So, that term does not appear here. So, probability of a concept, if for example, we use conceptual category from ROGET'S thesaurus, then the formula will change this way on the joint probability. So, what is the use of this? The use of this is that we can obtain the parallel corpora, and from the parallel corpora it is possible to get the sense of the word as a translation, and this is guided by the probabilistic calculations which were shown on the slide. So, some remarks on unsupervised approaches to words and disambiguation. We see that if the approach is Lean's algorithm, we get a precision of about 68.5%. The result was considered to be correct if the similarity between the predicted sense and the actual sense was greater than 0.27. Recall is not reported. Corpus is trained using Wall Street Journal corpus containing 25 million words tested on 7 SEMCOR files containing 2832 polysemous nouns. The baseline accuracy is 64%. So, there is a 4% improvement. Hyperlex algorithm has a high accuracy about 97%, recall is 82%. Tested on a set of 10 highly polysemous French words, baseline accuracy is 73%. So, there is about 25%, there is an accuracy improvement of about 25 points. YAROWSKY'S algorithm for WSD using ROGET'S thesaurus, the accuracy is 92%, tested on a set of 12 highly polysemous English words. Baseline accuracy is written as not reported, but it would be easy to calculate because this comes from the first sense of the wordnet. Worsened disambiguation using parallel corpora, we have here the accuracy values 62%, 67% when the senses are concerned and when the concepts are concerned. It is trained using an English Spanish parallel corpus, tested using SEM-eval2, all worst task. Baseline is not reported. So, in general we can say that unsupervised worsened disambiguation algorithm has a lot of interest in the community because sense mark corpora is so difficult to obtain, but these algorithms are difficult in terms of high accuracy, in terms of achieving high accuracy and in terms of producing the labels, but this would be good for languages whose resources are scarce.